Shamanta MS, Assistant Professor in Physics Department from Maharaja Institute of Technology. In this session, I am going to explain the other type of oscillation. Till now, you studied the free oscillations, that is SHM, how the simple harmonic motion will execute, that is when the only restoring force acting on a body. But if we take the other oscillations, when the forces will be increased, that is more than one force. Now the restoring force and resistive force, resistive force or frictional force or retarding force. So when that force is acting on a body, how the oscillation will goes on decreasing. So that is nothing but damped oscillation. So damped oscillation, it will says that when the resistive force acting on a body, then the amplitude goes on decreasing. Then finally it will fades out. So that is nothing but damped oscillation. So, damped oscillation means any oscillation in which the amplitude goes on decreasing within a short time interval and completely it fades out. So along with the time. So when the time is varying along with the displacement, so the amplitude goes on decreasing and completely it will terminate. So that is nothing but we used to call as a damped oscillation. So any oscillation in which the amplitude goes on decreasing, which the amplitude goes on decreasing. Amplitude goes on decreasing within a finite interval of time. So and completely it fades out. So the amplitude is maximum initially, then after that when the resistive force acting on a body, then it start to goes on decreasing and at last completely it will terminate, it fades out. So that is nothing but damped oscillation. And also one more we can say in another way, when the restoring force and frictional force acting on a body, then the motion of the body will get terminate, or it will, while it coming back to its equilibrium position, the amplitude goes on decreasing. So that is also called as damped oscillation. So then what are the examples for damped oscillations? So all the mechanical oscillations in simple pendulum. So examples, if we means what will happen when a spring is attached with the mass, when you used to keep in a liquid, in any liquid, keep in a liquid or in air, okay. So then its amplitude goes on decreasing and completely it will terminates. So compared to air, in liquid the motion of the body will quickly come to its mean position. As quickly as possible it will come to the mean position in liquid. So these are the examples for damped oscillations. So next, based on this we are going to find out the differential equation for the damped harmonic oscillation. Differential equation. First, which are the forces acting on the damped oscillation? So that the forces acting on damped oscillation. first. The first is restoring force. So, the restoring force, this opposite to the motion of the body. So, that is why we are writing in terms of negative. This negative indicates that the opposition motion of the body. The force is acting opposite to the direction of motion of the body. When we remove this proportionality constant, so that we used to represent it by a k minus ky, where k is the proportionality constant. K is proportionality constant. Proportionality constant. So, next one more force, that is resistive force. Resistive force or frictional force. So, this restoring force, what is the restoring force? We can represent that as by Fr, and the next is frictional force or resistive force. Frictional force is directly proportional to the negative of the velocity. Negative of the velocity. When we used to remove this proportionality constant, then that used to represent it by as is equal to minus r into dy by dt, where r is the damping constant, proportionality constant, that is called as damping constant. So, this negative sign indicates that the frictional force which is acting opposite to the direction of motion of the body. So, these two forces which is acting on the body, so then the damped oscillation will takes place. So, now we have to consider, by considering these two forces, we have to derive the differential equation. Then after that, for that, what is the solution? Okay. So, now consider, once again consider these forces which is acting on the body. So, if m is the mass of the particle, m is the mass of the particle, mass of the particle, and d square y by dt square is the acceleration. Acceleration acting towards the mean position, and the velocity dy by dt is the velocity. So, then consider the force which is acting on the particle. So, that we can represent as here restoring force plus frictional force. So, the damped oscillation, it is the combination of restoring and frictional force. So, restoring force means we know that is when the m is the mass of the particle, a is the acceleration due to gravity. So, then we can write this as m into a. So, m into a, and the frictional Fr is equal to minus ky, and what is the frictional force acting here, that is minus r dy by dt. So, this acceleration, where a is the acceleration due to gravity, d square y by dt square. So, that is why we can write this as m into d square y by dt square is equal to minus ky minus r dy by dt. Okay. So, just bring that m to the right side, then we will get the equation, that is d square y by dt square is equal to minus k by m into y minus r by m into dy by dt. So, this equation can be written as d square y by dt square plus k by m into y plus r by m dy by dt is equal to 0, where d square y by dt square, this k by m considering as a omega square y, and this is b, dy by dt is equal to 0. So, that means where omega square is equal to k by m and r by m is equal to 2b, where omega is the angular frequency and b is the damping coefficient. Omega is angular frequency. Angular frequency and b is damping coefficient. So, this is the differential equation. So, name it as equation number 1. So, this is the differential equation of dampered oscillation. Consider differential equation damped harmonic oscillator, that is d square y by dt square plus what we get omega square dy by dt omega square dy by omega square y plus 2b dy by dt is equal to 0. Okay. So, this is the equation 1, what we got, just name it as equation 1. Now, to solve this differential equation, assume to solve equation 1, assume the solution is y is equal to a into e to the power of alpha t. Okay. So, just assume the one solution and next find out the exact solution for the damped harmonic oscillation. So, first differentiate with respect to time t. Differentiate with respect to time with respect to t. So, then what we will get, dy by dt is equal to a into e to the power of alpha t. So, with respect to t, so then what is the coefficients, that write it here alpha, then name it as equation 2 and again differentiate, then what we will get, d square y by dt square plus, so a into e to the power of alpha t, alpha we will get once again differentiation, then one more alpha, that is alpha square. Name it as equation 3. So, next by substituting equation, this equations by y value we get this equation 3, then what we will get, a into e to the power of alpha t alpha square plus omega square a into e to the power of alpha t omega square a into e to the power of alpha t plus 2b dy by dt, that is a into e to the power of alpha t into alpha. Okay. So, that is equal to 0. Now, what is the common, take that outside, then what we will get common. So, a into e to the power of alpha t is common here. So, that is why we will get the remaining alpha square plus omega square plus 2b alpha is equal to 0. Okay. So, here the exponential term is there and one more is quadratic equation form. This exponential term, that is never equal to 0. So, that is not equal to 0, and the another quadratic equation. So, that is right in the higher order terms, alpha square plus 2b alpha plus omega square is equal to 0. So, this is in quadratic equation form. To solve the quadratic equation, we know the formula, that is alpha is equal to minus b plus or minus root of b square minus 4ac divided by 2a. So, what are the coefficients of a, b, c here in this quadratic equation? So, a, here the coefficient of this is a is equal to 1 and b is equal to 2b and c is equal to omega square. So, write that values here, then what we will get? Alpha is equal to minus 2b plus or minus root of b square value is 4b square minus 4 into ac, a value is 1 and the c value is omega square divided by 2. Okay, so here the square root of 4 value is 2, that we can take it common, then what we will get? Alpha is equal to minus 2b as it is plus or minus 2 root of b square minus omega square divided by 2. Okay. So, then further how we can solve this equation, that is, so we can take the common outside here, 2 common, then the remaining term is b plus or minus root of b square minus omega square divided by 2. So, then the 2 will get cancelled. So, we are getting the 2 solution here, plus or minus. So, that we can be written as, that can be written as so what we are getting, alpha is equal to minus b plus or minus root of b square minus omega square, right. So, this can be written as constant, that alpha 1 is equal to minus b plus root of b square minus omega square, alpha 2 is equal to minus b minus root of b square minus omega square. So, here we are getting in terms of plus and minus 2 values. So, now we have to substitute this alpha values in the assumed solution. So, we can write that assumed solution. So, what is that assumed solution? Assumed solution is y is equal to a into e to the power of alpha t. So, that can be written as, that can be written as we can be written as y is equal to a into e to the power of a1 alpha 1 t plus a2 e to the power of alpha 2 t. Okay. Now, substitute that alpha 1 and alpha 2 value here, and where a1 and a2 are arbitrary constants. So, we have to find out the solution for these arbitrary constant. So, then we will get the complete solution for dampered harmonic oscillator. Okay. So, now substitute the alpha 1 and alpha 2 value here. Substituting alpha 1 and alpha 2 values. So, we get y is equal to a1 e to the power of alpha 1 value is minus b plus root of b square minus omega square into t. plus A2 e to the power of minus b minus root of b square minus omega square into t. So, then this is name it as equation number 4. Name it as equation number 4. Now, to solve this arbitrary constant value, we can by using initial conditions that is at t is equal to at time t is equal to 0, the amplitude, the displacement y is equal to y naught, and the velocity dy by dt is equal to 0. So, if we substitute these values in the above equation, so then the equation 4 will become equation 4 becomes y is equal to a1 plus a2, because exponential of power 0, that value will be e to the power of 0 is equal to 1. So, this whole first starting term it will become completely 1. So, that is why we will get y is equal to a1 plus a2. So, then this equation can be written as, we can for our convenience, so we rearrangement that has a1 plus a2 is equal to y, and this name it has equation 5. Name it has equation 5. Now, so again we know the values of the, now differentiate equation 4. Equation 4. So, the equation 4, then we get, if we differentiate equation 4, dy by dt is equal to a constant, write it as it is a1 exponential minus b plus root of b square minus omega square into t. So, what is the coefficient of the t? We have to write it as it is. Then what we will get, minus b plus root of b square minus omega square, and in second term that is plus a2 e to the power of minus b plus root of b square minus omega square into t, and the second term what is, write it as it is, that is minus b minus root of b square minus omega square. Okay. So, from initial conditions that we know dy by dt is equal to 0, then, and so initial condition from, we know that from initial condition dy by dt is equal to 0, and at time t is equal to 0. So, what we will get, 0 is this last this equation will become 0 is equal to a1 e to the power of, that term will become 0, and this write it as it is minus b plus b square minus omega square, and in second term a2, that e to the power of 0 it will become 1, then what we will get, minus b minus root of b square minus omega square. So, this e to the power 0, this will be tends to 1. Then in first term here, if you observe here, minus b is common. So, if we take that minus b common outside, then what we will get, 0 is equal to minus b, then a1 plus a2. And in the second term, if we observe in the second term, so what is the root of b square minus omega square is common here. So, take that root of b square minus omega square outside, then what we will get, root of b omega square, then we will get a1 minus 8. Okay. So then what we will get, so that is y naught. So therefore from equation 5, the above equation will become 0 is equal to minus b y naught plus root of b square minus omega square into a1 minus 8. So next we can write it this as a1 minus a2 is equal to a1 minus a2 is equal to this will become by naught is equal to root of b square minus omega square into a1 minus a2. This the above equation will become a1 minus a2 is equal to by naught divided by root of b square minus omega square. Okay. So this is, name it as equation 6. Name it as equation 6. Now we have to add equation 5 and 6. Then we will get a1 value, and when we subtract the equation 5 and 6, then we will get the a2 values. So that we have to find out now. So here now first add, by adding equation 5 is, just remember that equation 5 is a1 plus a2 is equal to y1. a1 plus a2 is equal to y naught is equation 5. Now by adding equation 5 and 6. So what we will get by adding equation 5 and 6, a1 plus a2 plus a1 minus a2 is equal to y naught plus by naught divided by root of square. Okay. So here the a2 will get cancelled, plus and minus it will cancel, and then this it becomes 2a1. Y naught is common here, so that we can write it as 1 plus b divided by root of b square minus omega square. So what is the remaining term, that is. Then from this the a1 will become is equal to y naught by 2 1 plus b square minus omega square. So similarly by subtracting equation 5 and 6, so we get a2 is equal to y naught by 2 of 1 minus b divided by root of b square minus omega square. So these are the arbitrary constant values. Now we have to substitute this a1 and a2 values in assumed solution, that is y is equal to a1 e to the power of minus b plus root of b square minus omega square into t plus a2 e to the power of minus b minus root of b square minus omega square into t. So now substitute this a1 and a2 value in this. Substituting a1 and a2 value. So we will substituting a1 and a2, we get y is equal to, so y naught by 2 is common, so that we can write it outside. Then the remaining, so a1 is 1 plus b divided by root of b square minus omega square, and e to the power of minus b plus root of b square minus omega square into t plus a2 that is already we took common. So 1 minus b root of mass into e to the power of minus b minus root of b square minus omega square into t. So this is the solution for damped harmonic oscillator. So this is the solution, complete solution for damped harmonic oscillator. So this is the damped harmonic oscillator solution. So when the particle is executing with the velocity dy by dt and with mass m. So where b and omega are the relative values. So based on these relative values, the damped harmonic oscillator is classified into different cases based on the b and omega relative values, damping coefficient and angular frequency. B and omega relative values. So based on the b and omega value, this damped harmonic oscillator is classified into 3 cases.